Okay, so let's get started, shall we? So I saw some of you were confused when entering the classroom. Did I come to the right class? Well, you probably did come to the right class. I'll be teaching the second part of EE4210, and we'll be following from the application layer. And the many things we'll see with me is related to application layer. We'll start with application layer protocols, and then look into socket programming, which is the interface between the application layer and the transport layer you learned before. Hello. And then we are going to look at wireless and mobile networks. We're going to look at multimedia. And then finally, we're going to look at network security. And these chapters that I will teach define this module differently from the other computer networks module. We focus more on the application layer side, right? So first, a little bit about me and the lectures, the rest of the lectures that we'll see. So my name is Utku. So you can call me just Utku, or you can call me Dr. Tefek if you're not comfortable calling my name. I'm not a professor here. I'm an adjunct lecturer. But if you want to call me a professor, you can call me prof, however you're comfortable. So my main position is in Advanced Digital Sciences Center, shortly ADSC. So it's in the CREATE building. I'm sure many of you saw that CREATE building in Newtown. So we are a research institute on one of the floors of CREATE. It's a research center established by UIUC, University of Illinois in Urbana-Champaign. So we do research on cybersecurity, mostly cybersecurity on industrial control systems. Hello. So the things we do are to secure these old legacy systems, like the MRT system, first established in the 80s or 90s, or the power systems. Again, these were power plants, power generation. So these systems were not digital earlier, but now they are being digitalized. And because now they have a lot of attack surfaces due to being digitalized, they need additional security. So this is what we do. We add security onto these legacy systems without making a lot of structural changes on them. Yeah, so here is my website. You can check it out. And you can always email me at my NUS email here. So I did my PhD in NUS. I'm an NUS alumni, like you are, like you will be. And my bachelor's degree is from Bilkent University in Turkey. So my research interests are in communication systems and networks. So this was mostly during my PhD. Now I'm mostly focused on cyber-physical system security and applied cryptography. And so if you like to do an internship or a final year project with Advanced Digital Sciences Center on the topics I discussed, we also work around topics like industrial control system security, but mostly on security. Although we have a small AI group, you can also choose that. So please contact me. We have projects time to time. We might find something suitable to your interest. Hello. So I'll follow BIPLAB's protocol. I'll start the lectures at 10:02 on Wednesdays and 4:02 on Fridays. I suppose this was the protocol earlier? Okay. Yeah, I saw some of you coming late, so I'm wondering if he was starting later. If that is the case, let me know. So I'll try to release the slides in the PDF format before the lectures. I'll try to do that, but no promises that the slides that I show in the class will be exactly the same with the slides I upload. There might be small differences. This is not to hide anything from those who are not attending, but simply because I may correct something in the slides, or I might intentionally hide some information to ask it to you during the class. But I'll reveal it during the class. And you won't be missing anything by just following what you have uploaded on Canvas. And this is the most important point. Please feel free to ask questions. If you didn't understand something, well, the chances are others also didn't understand that. So you won't look like a fool, but you'll look like a hero because you're clarifying that point your friends didn't understand. And I think this is the best advantage that we have, that you can ask questions, that we can interact. Because frankly, I mean, this class is a very common class. You can find a lot of resources online. You can find a lot of books. Even you can check the Krause and Ross website, the authors of the textbook that we are learning here. In their websites, you have video presentations for most of the things you're learning here. You can check those out. And these guys are probably teaching much better than I do. So I'm not very, I'm not pushy on you coming into the lectures. But if you're coming here, I think there is one advantage that we have over these guys. Now you can ask questions. Now I can clarify points you don't understand well, right? So this is the most important point, I think. And I'll follow the same tutorial format, the releasing questions first, giving you 1 or 2 weeks to solve, attempt the questions, then I'll solve them. I'll solve them in the class. A little bit about CA2. So this is going to be a socket programming assignment. Don't worry, we are going to learn about socket programming. And you can use any programming language of your choice here. Well, in the last year's CA, it was pretty easy. But I think this year it's going to be considerably more difficult. Because you know what happened? I gave last year's assignment to ChatGPT, and it did it very well. So I'm sorry, but as computers get smarter, you have to get smarter as well. So this year it's going to be a little bit more difficult. I haven't decided on how to make it more difficult. I want to make it very tedious to read as well. So I'll release more details on that. Luckily, we have maybe a couple of weeks until I release that, until we learn about socket programming. But the main point here is that you can expect considerably more difficult CA2 if you somehow obtained or learned about your friends about last year's assignment. So this is what you learned in the first part with Biplab, right? And in the second part, well, the durations are tentative, but they're going to start with application layer. They're going to look at some of the widely used application layer protocols and how they interact with the transport layer below that you just learned earlier in the second chapter. Then we're going to look at socket programming. This is how application layer interacts with the transport layer. It is going to be very short. I'll teach it in Python. And I think most of you are familiar with Python than any other programming language. But again, you can use any language in the CA. You don't have to stay with Python. But it's just easier, in Python. And then we're going to look at wireless and mobile networks for about 1 week. Then we're going to look at multimedia networking. So this is how video, voice, and that kind of data is transferred over the networks. And then we are going to look at network security. Compared again to last year, I increased the load in the network security because I feel that is the chapter the students are most interested in. And I also think this is the chapter I can put some of my insights into it because that is my research area as well. All right, so any questions up to this point? About the assignment, about the protocol of the lectures, about me, anything? Yes, please. I'll give around 1 month. Okay? By the way, I can make it a duo assignment. You can do it in groups of 2 or groups of 1. What do you prefer? not groups of one, just as a single person, of course. Who prefers doing it alone? By the way, before you raise hands, let me also say this. If I make it a duo assignment, it's going to be more difficult, no doubt. Maybe twice as difficult. So you do the same job. Who wants to do it alone again? Okay, more hands. Who wants to do it with a friend? Okay, less hands. Sorry. It will be single assignment then. Okay, any other questions? All right. Okay, let's get started with the application layer then. So the application layer is where it all begins. So this is the reason for the existence of the underlying network in the first place, right? We have all these networks because we have applications that we want to run on different end systems. For instance, you have your mobile device, which runs many applications, and that communicates with the mobile applications web server or another mobile device through all this network in between. And all these network elements are the ones you learned previously. And now we are looking at how these network elements, namely the transport layer, interacts with the application layer, and what common application layer protocols are there in the web or in the internet in general. First, we are going to look at the web and the web's application layer protocol, HTTP, Hypertext Transfer Protocol. So this is indeed the protocol being used when you browse over the web. So when you open a website, when you write a URL into the URL field of your browser and connect to a website, it is indeed using HTTP. You're sending an HTTP request to the web server, and then the web server responds you with an HTTP response message. And thus you see what you see on the browser, the content of the website. Then we are going to look at electronic mail, SMTP, the Simple Mail Transfer Protocol. The popularity of this has been diminishing. This is now still being used between the mail servers in the web. But sometimes HTTP is also preferred for electronic mail. And then we are going to look at DNS, the domain name system or the domain name server. So this is when you write a URL, it converts it into an IP address. It does a few more things, but this is the main thing it does. It makes name IP translation or resolution. So we recognize each other with names, right? You can call me Utku, but you don't know my NUS ID number or the staff number, whatever. It is very difficult for you to memorize each other's number. But in the internet, because everything is in numbers, the machines recognize themselves with addresses. Like in the network layer, you learned about it. You learned about IP addresses. And in the link layer, you learned about MAC addresses. And this DNS is what stores and translates these names into IP addresses and vice versa. All right? It does a few more things, but we'll learn about them later on. And about HTTP, let's also not skip this. We are going to learn how it is very human readable, and we are going to learn how to read and understand HTTP messages. Okay, so we will start by looking into services provided by the transport layer right below. Because anything the application layer does can only be done using the services provided by the transport layer. So it is like this one. So let me give an example. So this mailing example is given very commonly. I'm sure you've heard of it before. You're writing a mail, a physical mail to your friend. You are writing it with a pen. you're putting it into an envelope. This is the application layer. You have to know how to put it in an envelope. You have to know what to write in the envelope, the address of your friend and the name of your friend. This is like the IP address and the port name of your friend, of the web server. And all you need to do is to know how to transfer it to a transport service provider, to a transport layer. So this is, for instance, a delivery service, or something like SyncPost. All you need to know is how and where to put that letter, which is the SyncPost box. And you also make sure you write the address, the correct address on it. So we are going to start by looking into services provided by the transport layer, how transport layer interacts with the application layer, okay? Then we are going to look at the client-server paradigm and peer-to-peer paradigm. So in the web, if a client is communicating to a server, this is called client-server paradigm. And if two clients are communicating with each other, this is called peer-to-peer paradigm. We are going to learn details on this. And then we are going to look at popular application layer protocols, like the web's application layer protocol, HTTP, the simple mail transfer protocol. And because SMTP is only a push service, again, we are going to learn, don't worry about it just yet, these POP3 and IMAP are also used to pull things from the SMTP servers. I'm sure you're familiar with these names, although maybe you don't know what they do when connecting to when integrating your mailbox into your new PC. You probably use things like this. You've seen POP3 and IMAP. And then we're going to look at DNS, as I said earlier. So these are some of the network applications we use daily. So we use email every day. We use web browsing every day. We use text messaging again every day. So remote login is logging into a computer remotely. P2P file sharing like torrent. And we play multi-user online games, streaming stored video from web servers. We use voice-over IP applications like Skype. We use real-time video conferencing like Zoom. And there are social networking applications, most of which run on, again, the web, or mobile applications, which may or may not use web. And we also have internet search. So what's really interesting here is that many of these applications that you see here were invented, or let's say developed, long after the internet architecture was developed. So the early internet architecture was developed in the 70s and 80s, and the inventors of the internet didn't know most of these applications are going to be in place. But they still work on the internet. So this is kind of amazing to me, because think of it like this. You have no automobiles. Let's go back to 19th century, early 19th century. It's like you have no automobiles. You only have carts run by horses, and people are riding horses. But you're still building highways and all these bridges so that the cars, the automobiles coming 100 years later are using them no problem. Of course, the capacity has improved, yes, but the protocol, the main internet protocol known as TCP/IP, remains the same, and it can support. It also developed a bit, but the main architecture is still the same. So all the layers you learned about so far and the transport layer abstractions you will learn in this chapter, again, developed long before these applications. So that means the designers of the internet, namely the TCP/IP architecture, got it right. So the network they invented supports all kinds of applications they probably haven't even imagined. So let's now hear one of the inventors of the internet, Windsurf, says about it. I hope it runs. Okay, great.
So that's a long way of saying that we actually had some appreciation for what this technology could do. And we used it to do a lot of the applications that we still use today: electronic mail, file transfer, remote access to time-shared machines. But of course, the most significant change after the internet finally gets operational in early 83 and then becomes commercially available in 1989 is Tim Berners-Lee's development of the World Wide Web. And to be honest, Tim releases this out of CERN in Geneva in sort of December of 1991. Nobody notices, except for a couple of guys at the National Center for Supercomputer Applications, Mark Andreessen and Eric Bina, who say, oh, this is cool. Why don't we build a graphical user interface? So they develop the Mosaic browser. They release this. It makes the internet look like a magazine with formatted text and images and eventually, audio, video, and things like that. Everybody notices, including Jim Clark, who had been the founder of Silicon Graphics, which was a heavily used machine for computer-generated graphics in the movie industry. So Clark drags these guys out to the West Coast and starts Netscape Communications around 1994 or so. They go public in 1995. The stock goes through the roof. The dot boom is on. Every venture capital guy is throwing money at anything that looks like it might have something to do with the internet. This continues for 5 years or so, and then in April of 2000, everything falls apart and the dot bust happens, except in that period of time, from 1989 as commercial service gets started to that period in 2000, the internet is growing at 100% a year, and it continues to grow, not today, at that rate for a while, not today, but still growing. And so this introduction of this new way of sharing information on the net had a profound impact on its accessibility and utility. What we had achieved is this infrastructure that was infinitely, well, not really, but largely expandable. It dropped the barriers to access to computer communication to as close to zero as possible. We had given away the design of the internet for free with no patents or any other constraints deliberately in order to stimulate adoption and use. So as the general public encounters the World Wide Web, they have the ability to inject content into the network with very little barrier, and of course to get access to that information. In fact, there was such an avalanche of content that flowed in that we now couldn't find anything, and we needed search engines. So we got things like Alta Vista and Yahoo and eventually Google, Bing, and so on. So this question of did we know what was going to happen? No, but there were milestones in the course of the evolution that signaled that this was going to be a big deal. And it was the commercialization in 1989 of the service as opposed to commercialization of the equipment like packet switches from Cisco Systems or Proteon or others. It was the commercialization of the service and the arrival of the World Wide Web that really conflated these two things. Then there's one other thing which I think was equally significant, and that's the arrival of the smartphone in 2007. This is Steve Jobs and Apple. And this is very interesting because the mobile phone design work was started in 1973 by Marty Cooper, who was at Motorola at the time, which is ironically the year.
Okay, then he goes ahead and explains how internet-enabled smartphones and how smartphone made the internet more accessible. Oops. You can watch this interview later on YouTube, so you can just click on that link above. Okay, now any questions up to here before we get really deep and started into application layer? Okay. So let's start with an analogy here, or just an example here. So let's say you're a programmer and you want to write a mobile application or a web application. And obviously, your application needs to run on different end systems, right? If it is a mobile application, on one end, it needs to run on a mobile device, and on the other end, it needs to run on a server. If it is a website, it runs on a computer's browser, which is the client program, and the other part runs on a web server. So they need to communicate over a network, namely the internet in this case. So how do you go ahead? Do you actually write the programs for all the devices involved, namely the client device, the server device, and all the routers and all the switches in the internet, everything? Well, obviously, you don't do that. You can abstract away all the complexity happening deep inside the networks. You don't need to write software for the network core devices. They do not run user applications anyway. They only have up to maybe a link layer or at most network layer protocol stack. And what is the benefit of this? Obviously, it allows rapid app development. Instead of programming everything in between, all you need to know is how these end devices work, how to write programs for them, and how your program interacts with the transport layer. That's it. In other words, you write the API, the application programming interface, between your application and the transport layer. So you show how API looks like to these transport layer services and what services are provided by the transport layer. That's all about it. So if you're, are you familiar with API, the application programming interface? Okay, let me explain. So by an analogy, let's say you're in a restaurant and you're giving orders. It's a bit too loud. You're giving orders to a waiter, and this waiter relays your order to the chefs. So this waiter here is like the API between you, the person giving the order, and the kitchen, the chef's cooking and running another process. So there are two different processes going on, and the transport layer API is like the waiter who relays that information. And in software development, we have a lot of these APIs, because it enables different applications to interface with each other. Another example could be, let's say you're a quantitative analyst firm, and you want to read data on the Singapore Exchange. And Singapore Exchange has an API provided for you to tap into SGX data. So instead of knowing what's going on in the SGX, instead of reading all the company announcements whatsoever, all you need to know is how this API works and how this API interfaces with my application. That's it. So it allows, again, rapid app development, and it makes it easier to integrate different software applications. So yeah, you don't need to know anything beyond the application layer and how application layer interacts with the transport layer. All these services are provided by the core network, and you do not write software for them when creating a network application. I mentioned about a couple of application architectures, client-server and peer-to-peer applications. So now we're going to learn about these. So in the client-server architecture, it's like if we give an example of the web, it's like your browser on one end, which is the client application, is communicating with a server application running on a web server. So the difference between the client and server is like this. Servers are always on. So you know their IP address. They have a permanent IP address. So once you want to connect with them, you know that IP address and you type it into your browser, the client application. And the client application then sends an HTTP request to that server over the network, and then you get a response from that server. Again, how does that URL you write is translated into IP address? That is DNS, and we're going to learn about it later. Don't worry about it yet. And servers typically use, instead of user devices like ours, they typically use data centers for scaling. So think of it, think about Netflix, for instance. If Netflix only had one server in the US, what happens when you try to stream some video over the Netflix CDNs, the content delivery network, is that that data needs to go all the way from the US to Singapore. And it needs to happen for every request around the world. Instead, these web services typically use data centers for scaling. So data centers are like supercomputers, and they are distributed across different management domains. So they are usually closer to different users around the world. By the way, this is for the large websites, like the Netflixes, like the Googles. For your personal website, it can run on a single computer, like even your home computer. But if this is a critical application, like a big shopping website, like a streaming service or a gaming server, they typically run on the data centers for scaling. And clients, on the other hand, to communicate with the server, they can intermittently connect and disconnect, and their IP address might change. In fact, your laptops may have an IP address here, and it might change once you go to home. So you don't have a permanent addressable IP address, and you can be off at times. So once somebody wants to connect with your device, it may not be possible all the time. And in the client-server architecture, the main difference between the peer-to-peer and client-server is that clients do not communicate with each other. This is one of the main differences. Clients only communicate with the server in the client-server architecture. In the P2P architecture, peer-to-peer architecture, on the other hand, there is no always-on server. Basically, clients are communicating, and because they're not always on, there is no always-on party here. Here, arbitrary end systems directly communicate. It's like this. Let me show with a pen. So it's like this device can communicate with any of these devices in another network domain. And they can request and provide services from and to each other. An example, again, is maybe a torrent application. Once you join a torrent application, you start downloading data from other clients. This is peer-to-peer, directly coming from other clients. But you also provide services for them by storing that data and sending to the ones requesting that file. So every incoming user brings additional capacity in addition to the additional demand it brings. So what does it entail? It brings self-scalability. Instead of a client-server application where when you increase the number of clients, the server may get overloaded. You only bring demand when you bring clients. But in the peer-to-peer architecture, when you bring additional clients, along with the demand you're bringing, you're also bringing capacity. Here, again, the peers can be intermittently connected, and they might change their IP addresses if they move around or if they're using dynamic IP type of protocols. But the peer-to-peer is not as commonly used in the web. So one reason for that is complex management. But I think an important reason is the security. It is very hard for you to ensure about the identity of the other guy here. Once you are connecting to a server, you probably know what that server is, which company that server belongs to. But in the peer-to-peer, you can, it is not really easy to ensure you are communicating with the right entity because you don't know the counterparty in the first place. Okay, any questions up to here about client peer-to-peer and client-server architectures? Okay. So now we are going to learn about processes. So process, you can think of a process as an executing version of a program. So let's say you wrote a program, you did some coding, and you compile that code into a program, right? So this is a program as it is. But once you run that program, once you instantiate that, it is now called a process running on a computer, okay? So process is program running within a host. Host meaning any device, any computer. So if we are within the same host, let's say your computer, and you're playing a single player game. If this process is running, if two processes are running in your host when playing the game, this is defined by inter-process communication. It is defined by your operating system. For instance, in a game, some processes are taking input from your keyboard and the mouse, and there is another process rendering the game onto your screen, maybe using ray tracing. And there may be another process that computes stuff in the game. Once you hit someone, how many hit points left, what damage that guy deals, and so on. So these are defined by the OS, and this is inter-process communication. But if you are talking about processes running on different hosts, they communicate via messages. So the messages are what goes through the network. So again, continuing on our example of gaming, let's say now you're playing a multiplayer game. So in addition to the earlier processes that communicate via inter-process communication, now your host is communicating with a web server to send your actions, right? Where you moved, what skill you used, and so on. And then in turn, the web server computes based on all the user's actions. It communicates with all the other hosts and gives you the result. Now, what happened to you, how many hit points you're left with. And these processes that enable these end systems, the server and the client, to communicate are defined by exchanging messages. So your client application, some process in the game, communicates with another process in that web server. And in the process communication, there is also a significant distinction between the clients and the servers. So the client process is always the one that initiates communication. So in a web application, you always send an HTTP request message first so that the server knows that you request something. Because you are the only one that you're the only one who knows that the other party is always on, right? It has a permanent IP address. You know that it is always on, so you need to request that. So if you are here and you have some business with the EC department, let's say, it's not like EC department sends someone to talk to you, right? You know their place. You know that they are online, if this is within the office hours. So you go there and deal your business. But it's not the other way around. Always the client requests something from the server, and then the server responds. And the server process is the one that waits to be contacted. But if you're talking about P2P architectures, they can also have client and server processes running on them. So instead of defining a different architecture here, even in the P2P applications, one peer is the one requesting, another peer is the one responding. Okay? Okay, before we go into sockets again, any questions? So these concepts are important, and I'm going to be using them throughout the rest of the application layer. So make sure you understand them well at this point. Okay. So now let's learn about sockets. So the application programming interface, the API, down the transport layer uses sockets. This is the way application layer interacts with the transport layer below. And this is analogous to a door in a room. So you run applications in the room, and you send it out of the door. It's just, the door is like the socket. Or the earlier example I gave, you're writing a mail and you send it, you put it into the SyncPost mailbox. That mailbox is like the socket. And here the sending process sends the message out of the door, and it relies on a transport layer infrastructure on the other side of the door to deliver the message to socket at the receiving process. So just like you're sending it through the door, at the receiving end, there is another door, another socket, and it goes up there, up from the transport layer to the application layer. So you can see that in this picture. So the sender process shows it out of the socket. It goes through all the layers here, and then it goes through the internet, and it goes back above all the layers one by one, and sent from the transport layer to the application process. And again, only the application process and how it uses the sockets are controlled by the app developer. The rest of the layers are controlled by the OS, and when the packet is within the internet, again, all this is controlled by the core network devices, so you don't program them. All right? So to communicate with somebody, you need an addressing information, right? In a mail, you write the address, and in addition to the address, let's say the postal number, you also write the unit number. Or let's say you're calling a company, but you want to call a particular person in a company rather than the company as an entity, right? You know a particular person in the company, but if you call whatever number you find on the web about that company, you probably won't get that person on the line. You'll probably get some secretary of that company on the line. To communicate with that exact person, you need to enter an extension number. Again, here in addressing processes, IP address may not be enough. Why is that? Because when your client application sends a request to a particular IP address, at the other end of that IP address, at the other end of that socket, that IP address may have multiple applications, multiple processes running in them. And which process are you communicating with? So how do you determine what particular process you are addressing here? Well, the answer is the port numbers. So in addition to the unique IP address you are entering when sending a request, because there can be multiple processes running on the same host, the request identifier must include the port number in addition to the IP address. For instance, for the HTTP server, this is usually 80. So in addition to the IP address of the server, you enter port number 80. For SMTP servers, this is usually 25. So these are not always the case, by the way, but your books teaches them that way, so I'll just follow the book. But they might have different IP addresses. But usually the HTTP's port number is, at least it includes 80. And yeah, let's say you're sending an HTTP message to that web server, gaia.cs.umass.edu. You send, in addition to that IP address, to indicate that you're communicating with the web server through the web server running on that IP, but no other server. You include that port number 80. And in fact, we are going to demonstrate it using Telnet, how to connect to a web server. Okay, any questions up to here? Yes, please.
So with your architectures, so if something is using like a server process, that is just one of the peers operating like as like a running out of the server, because there aren't actually servers. Right?
Yes, correct. So yeah, that's a nice question. So when I say one of them acts like the server, it waits to be contacted. So it receives the request message, and then it responds. But obviously, it doesn't have to be always on, like a web server does, or it doesn't have to have a permanent IP address. Yeah, good point. Yeah, any other questions? All right. So an application layer protocol defines what types of messages are exchanged. Well, this is pretty similar to the protocols you learned earlier, whether this is a request or response message. And it defines the message syntax, what fields in the messages are, and how fields are delineated. It also tells you how each field is interpreted, the meaning of the information in these messages. And it also establishes the rules for when and how processes send and respond to messages. I won't delve too much on it for now because we are going to see how an HTTP message looks like. I think on a concrete example, it will be easier to understand. But one distinction we have is that in protocols like HTTP or Simple Mail Transfer Protocol, these are openly defined. These are widely available, and they are defined in the RFC documents, request for comments documents. So these are the publication series going on for decades from the principal development and standard setting bodies of the internet. Okay? But there are also some proprietary protocols like Skype and Zoom. They use proprietary protocols. They might use HTTP as well, but they also have their proprietary protocols in addition to them. And what's the benefit of using open protocols? Well, obviously, it enables interoperability. If you're using an open protocol, others can also build apps on your open protocol very easily. They can improve upon it. They can make changes on it, and so on. But if you're using proprietary protocols, you need to define your API. Otherwise, it is very difficult, usually impossible or not allowed to modify them. Okay, so now let's discuss. I earlier said that the application layer uses services from the transport layer, right? But what transport layer services in particular are provided to an application? So one property could be data integrity, right? Here, I don't mean integrity in the security sense. I don't mean intentional changes on a data, but this is just unintentional loss or corruption of data. So in some applications like file transfer application or maybe a banking application, right, on a web browser, they need data integrity. You don't want to send $5,000 instead of sending $50 to your friend. Or if you're getting a video, you don't want your video to be corrupted, otherwise you cannot even play it. So some applications require 100% reliable transfer, but things like audio can maybe tolerate some loss. Some applications may require timing. So some of the multiplayer games, the internet telephony, they require relatively low delay, maybe about 100 milliseconds at most. And some applications may require high throughput, like a video application, because you're downloading video data in a way. It needs to have really high throughput. But some applications are more elastic, like let's say you're downloading a file. It really doesn't matter too much if my file is downloaded in 2 seconds or 10 seconds, as long as I get it with full integrity. And in addition, we might need security. Again, in a banking application or any other website that we enter our passwords with, you don't want somebody to steal your data. That's one element of security, so you might need encryption. But there's also another element. You need integrity and message authentication. So integrity in the sense that you want to ensure that the message you're sending has not been modified by any unauthorized party before it is being received. And message authentication, the authentication, endpoint authentication, in the sense that when you're communicating with somebody, you know that the party you're communicating with is the one actually sending the messages to you, but it's not somebody else who replaced that person. Okay? So for the security, we are going to learn about that in the last chapter mostly, in the network security chapter. But let me ask you a question here. So apart from security, don't mind security yet, can we guarantee these using the correct transport layer service? In other words, can we guarantee data integrity? Can we guarantee throughput? And can we guarantee timing? What do you think? So let me remind you of the transport layer services. You learned about TCP, right? TCP provides reliable transfer. It has flow control. It has congestion control. What else? If a packet loss occurs, it makes retransmissions, right? You learned about it. So can TCP guarantee these? Well, obviously UDP cannot, but can using TCP guarantee all that? Come on, just some ideas. Okay, well, the answer is it can guarantee to some extent. Well, because it is, again, it is dependent on the underlying network infrastructure, whether there is sufficient throughput in the first place, or whether there is enough traffic allowed for my, or whether there is enough whether there is enough bandwidth for my application. Because there might be congestion in the network, there might be other traffic going on in the network. So the transport layer services like TCP can ensure reliable data transfer because it performs retransmissions. But it may not guarantee timing, right? If the network is heavily congested, there is no way using TCP alone is enough. Or if the network has insufficient bandwidth, using TCP is not enough. But can we guarantee these? Let's not say guarantee, but can we provide the guarantees provided by the TCP without using TCP? For instance, can I use UDP and ensure some form of guarantees on data integrity? Well, yes, we can actually. So what happens is in the application layer, you can define your retransmission protocol, like the TCPs. For instance, in a video application, usually UDP is used. Let's say UDP is used in a web server, and you're downloading video data, or you're streaming video data. You can build your application in a way that the missing video frames are transmitted to you. So you don't have to really use all the transport layer services you need. You can define some of them in the application layer. And if we come back to security, in fact, security is also provided in the application layer using, in the web's case, it is using transport layer security. So these are some of the popular applications and what underlying transport protocol they use. Well, email and the web and remote access, they all use TCP. File transfer also uses TCP because you don't want packet losses here. But again, streaming multimedia, it might use TCP or UDP. And commonly, UDP is being used because it is a lighter protocol. But even if you use UDP, you can build your application in a way that it still provides integrity guarantees. So again, if I ask then if TCP is better, why bother with even bother with UDP? Again, the response would be that we can build a lot of these services, a lot of these guarantees on top of UDP in the application layer. Okay. So Yeah, so in the vanilla TCP and UDP sockets, as I said, there is no encryption, there is no authentication, but the obvious drawback of this is that now the plain text passwords are sent into the socket and they traverse the internet in clear text. Obviously, you don't want that. And another problem is that once you receive a message from an application, you have no way of knowing that when receiving a message from a web server, you have no way of knowing that it actually comes from a web server, because anyone can attach the IP of that web server in the IP header and send you a packet. How do you know it is actually coming from that web server? So if this is the case, well, we cannot have a reliable internet. But luckily, we can build these security services in the application layer. Although it is called transport layer security, you implement it in the application layer. And it provides encrypted TCP connections. It also provides data integrity, making sure that your data has not been modified in transit. And it provides endpoint authentication to ensure that you're communicating with the entity that you intend to communicate with. So how TLS is implemented? Well, applications typically use TLS libraries that use TCP in turn. Typically, when you are developing an application, instead of you writing all the codes, you're writing all the digital signature codes yourself and calling RSA or ECDSA digital signatures, you simply use TLS libraries. It's all defined in there. So you just call these libraries, and so that your plain text is not sent, your data is not sent in plain text, but it is encrypted, and it is also provided with message authentication and integrity. Yeah, we are going to focus a lot on these in the last chapter, so this is just meant to be a little introduction on that. Okay, so before we start on the web and its application layer protocols, HTTP, any questions? All right. So, a web page consists of objects, and these objects are one base HTML file and one or more objects, or there may be no other objects, called by, or let's say referenced by that HTML file. So once you send a request to a web server hosting a web application like a website, you first send a request, and then the web server replies with that base HTML file. So your browser receives that HTML file, it parses it, and it sees all the other objects referenced by that HTML file. And then it can send a request to download the other objects. And after downloading them all, it displays you in the browser. So your browser here is your client application. So if you look at the example in here, we have some school.edu and some extension here, and this is the object. So each object in the website is also addressable by a particular URL. So if you only send a request to this, you only download the HTML file of this, and if there are any objects referenced in this HTML, your browser then requests them. But you can also access this whole thing, these individual objects in a website. Okay? So again, as I said, HTTP is the hypertext transfer protocol, and it's the web's application layer protocols, web's application layer protocol, and it runs on a client-server paradigm. So here the client is basically your browser running on your computer or your mobile device, and it requests and receives using HTTP protocol and displays these web objects sent by the web server, like so. So you send a request and you receive a response. Very simple. And the web server sends these response messages, again, using HTTP protocol, and it includes the objects you are requesting in the body of that HTTP response. Don't worry about the structure of those messages. We're going to have a look at them later. But yeah, it is very simple. You request and you receive a response. HTTP uses TCP as a transport layer protocol on port 80. Again, these are just numbers I'm giving because it is the most common one. There's nothing to memorize here. The server accepts the TCP connection from the client. Right. So the TCP is a connection-oriented protocol, right? So for HTTP messages to be sent and received, we must first establish a TCP connection. That's a must. And we first open a TCP connection. We send the request messages. The web server replies with the response messages. And when everything is fine, we don't have any other requests, we can close the TCP connection. It works like this. And we say that HTTP is a stateless protocol. And what we mean here is that server maintains no information about the past client requests. So whether you downloaded this object or that object, the web server doesn't remember. Which websites, which extensions you browsed, the web server does not remember. But let me ask you a question then. If the web does not remember that, how some of the websites can track you? They know what you viewed before. Yes? Yes, exactly. Yeah, we're going to come to that later. Okay, and the reason we want to make it stateless is that there are other ways to maintain state, like cookies. Or we don't even have to use cookies. Some of the websites have user accounts, right? For each user account, after you log in, whatever action you take, they can record. This is another way to do that. But obviously, for websites that do not require login, we can always use cookies. We want to make HTTP stateless because state protocols that maintain state is hard to maintain. They are complex. And if the client or the server crashes, they will have forks in their views of the last state. And even if they don't crash, just think about the client application, a browser. You can turn on and off your browser. You can turn off your computer even. So the maintaining state is not an option here. We are going to talk about two types of HTTP connections, non-persistent and persistent HTTP connection. Just like their names imply, in the non-persistent HTTP, it is not persistent. It keeps being opened and closed. It keeps opening a new TCP connection and closes it for every single request. So a connection is opened, an HTTP request response pair is sent, and then the connection is closed. And let's say you downloaded an HTML in that exchange, and you saw a few objects in that HTML. Well, you have to go ahead and open a new TCP. And then you need to send another request for each of these objects referenced in the HTML. So obviously, downloading multiple objects here required multiple connections, and it is inefficient in terms of timing overhead. To solve that problem, we have persistent HTTP. Here, we open one TCP connection, and multiple objects can be sent over that single TCP connection. Right? So you open a TCP connection, you request the first object, you receive the response, you see that in the HTML there are a couple of other objects. Again, you send another request, you receive a response, you send a request, you receive a response, and then when everything is done, you close the TCP connection. Okay? And persistent HTTP requires HTTP version 101, just some fun information. But it is, again, the most common one, and we are beyond HTTP 101. So almost all browsers that we use today can use HTTP 101. So they use mostly persistent HTTP if the server supports it. So let's go over an example for non-persistent HTTP first. So let's say this user enters this URL, that's some school.edu, some department's home.index. So this is an HTML file that contains references to 10 JPEG images. Okay? So here's what happens. So first, your HTTP client, which is your browser, initiates the TCP connection to the server, and the server at that website waits for the TCP connection at port 80. So it keeps listening on that socket at port 80. And once it requests the TCP connection request, once it receives the TCP connection request, it accepts the connection and it notifies the client. So, and then after that, the client sends the HTTP request message containing the URL into the TCP connection socket. And the server receives that request and responds accordingly. So it sends the HTML file in the body of the HTTP response message. So now the client received the HTTP packet. Here is still receiving. So this arrow here is for receiving the response message again. And then the server can close the TCP connection. That's it. If later the client sees that there are other reference objects in the HTML, it needs to open another TCP connection and repeat the same process over and over again for every single object. All right? So how many round-trip times here are involved? So I think you've learned about RTT, right? The round-trip time. So this is time for a very small packet of size that will incur no transmission delay to travel from client to the server and back. So 2 directions. So 1 round trip, okay? So 1 round trip time is spent for TCP connection. Here, we send a TCP SYN, we receive TCP SYN ACK, and then we can send an HTTP request. Well, I usually get some confusion here. So can you notice anything wrong in here, in this diagram? Well, we are sending a TCP connection request, and then we are receiving the SYN ACK message, and then we are sending a HTTP request message. Does it all look fine to you, or something is inconsistent here? Yes? Right, so yeah, thank you for that. So in the TCP, you learned that there is a 3-way handshake, correct? So there's SYN, SYN-ACK, and then ACK. Well, I think there are different views to that, but I'll just follow the book's approach. So your book says that the client can send the third leg of the HTTP, the third leg of the TCP handshake together with this HTTP request message. Okay? I have doubts as to whether that actually happens. Well, you can check over Wireshark if that actually happens, and let me know if you check that. I'll be glad to learn. But for this class, I'm just going to follow the book's approach and say that for TCP connection opening, we just spend 1 RTT here, 1 here, and we spend another 1 here. So in total, we spent 2 RTTs for downloading a single file using non-persistent HTTP. Okay? And obviously, if the file is not a very small file, you see that large block, there can be some time to transmit involved. So it is, in fact, 2 RTTs plus file transmission time. And, well, you can make that same argument about TCP connection closure at the end. Well, for closing the connection, why don't we spend another RTT in the end? Well, again, it's the same thing. Once we receive the file, we are done. We can initiate another TCP connection. That is done automatically at the transport layer. Your application doesn't spend any time on that. So if you want to send another HTTP request, what you do is you send another TCP connection request. You open the TCP connection. So this is for TCP. and then you send another HTTP request, and you receive HTTP response. So that's another 2 RTT for another packet. Okay, so another HTTP protocol is persistent HTTP. Obviously, non-persistent HTTP had issues that it requires 2 RTTs per object, and there is an operating system overhead for each TCP connection, which is ignored by your book, but there is some overhead. Browsers can open parallel TCP connections to fetch those objects, though. So that is one approach. I'll come to that later, but let's go over persistent HTTP first. In persistent HTTP, the server leaves the connection open after sending the response. Okay, so subsequent HTTP messages between the client server can be sent in that open connection. And the client sends the request as soon as it encounters a referenced object. So as little as 1 RTT for all the referenced objects. So if we see what happens here, so in the persistent HTTP, there is one for opening the TCP connection, and there is another one to download the base HTML file. Okay, so this is for downloading HTML. And in that HTML, the server solves, let's say, 5 referenced objects, and it sends another HTTP message for each of them. So this is times 5 plus the HTML. That is 6 RTTs plus 1 RTT to open the connection. Okay? That's it. Okay, so another question to you is, how can we make it even faster? So even in the persistent HTTP, we need to send 5 different requests for downloading every single object. How do we make it faster? Just any ideas are fine here. So you can be wrong. Don't worry about it. So here, as you see, we spent 1 RTT for opening TCP. We spent another RTT for downloading the base HTML file. And we spent 5 more RTTs. I was lazy to draw there, but there should be 5 more round-trip times there. How do we make it faster? So what does a computer do to compute things faster? How many cores do your computers have? Yeah, multiple. Just open multiple TCP connections. As simple as that. So what happens in that case? Let's say we can open, let's say, 2 connections in parallel, okay? So what happens then is, let me clear all that ink. In persistent HTTP, okay? Again, we have to spend, let's say this is my other connection here, okay? We spent 1 TCP connection. We spent 1 RTT for opening TCP in both of them. And in one of them, I have to download the base HTML. So before getting the HTML, I don't know what objects are there, okay? So for this one, I need to spend 1 RTT. And in that reference object, let's say, in that HTML, let's see I have 5 referenced objects, okay? So I'm now at this point, which already had me spend 2 RTTs, okay? And for the remaining 5 files, I'll just download 2 of them here, and I'll download 3 of them here. Okay? So how many RTTs in total? That is 2 plus 3. I got it in 5 RTTs. Okay? So again, important point to note here is that you don't know how many objects are there before downloading the base HTML file. So you can only do it on one of the connections, no matter how many parallel connections you have. Okay, any questions up to here in persistent and non-persistent HTTP? Okay, by the way, there is one other approach to make things even faster, and that is called HTTP pipelining. So that is beyond our scope, but if I quickly also show that. So here, what we do is, let's say I have a single persistent HTTP connection with pipelining. Again, I download my base HTML file, and I saw 5 referenced objects, right? Now, what I do is, instead of sending them one by one, I pipeline them. I send all of them back to back, spending no RTTs here. And then server immediately sends them back to me. So all I spent here is just 1 RTT instead of 5 RTTs. So I spent only 3 RTTs plus whatever file transmission time I incur. Okay? So this is commonly used in modern browsers. So we don't wait too much for download every single one of them. Yes? So how many objects are there is provided by the base HTML file. So you have to get it first. So that first red RTT there is to get that HTML file. And your browser parses that, sees the reference objects, and then only can send requests for the rest. Okay. Questions? Okay, great. So let's quickly look at what an HTTP request and response message looks like. Okay? In a request message, it is really very human readable. So this is a request message starting with the get. So get means I want to request this URL, index.html. In this case, this is the base HTML file. And I'm using HTTP version 101. This carriage return line feed is just enter. It's like entering. And my host is this. This is the web server's IP address. My user agent, my browser is Firefox browser. These are just some details, not that important. You don't need to include all of them in an HTTP request, but you must include the guest and the host. Whatever type of files it accepts, in this case it accepts text and HTML, the language is English, encoding is zip, the accepted character set is ISO whatever. Again, that is not important. What's important here is that what we are going to see very soon is this keep alive field. So this is for persistent HTTP connection. So the client, in sending this GET request, it wants to keep this connection alive, this TCP connection alive, so that in 115 time, whatever the unit of that is, it can send another HTTP request message or more. And then in the end, we have another carriage return line feed. So just marks the end of the message. So yeah, you don't need to memorize this, obviously. This is just an example. But you're going to use this in your socket programming assignment. So you can refer to this slide later on. Oops. And this is how it looks like if we parse them into a more readable format. You can check it out later. That's not really something very crucial here. But one difference is that, so in this example, there is no body. We don't send any data. It's only the GET request And the only thing we send is the host name and the directory that we want to download, the index.html. But in this example, you see an entity body. And this is used by certain methods, not with the get method, but with certain methods like the post method. So some web pages may contain, may require input from the user. For instance, some survey forms on the web that you fill in, they have fields that are requested from the user. In that case, in your entity body, in your HTTP post message, you include whatever survey you are filling in. You include the fields in the post in the entity body field here. Okay, we have already seen the get method, but in fact, we don't have to use the post method to send data to the server. Sometimes we can send that data within the URL field. So, in fact, if you search something on Google, you will be using the get method, not post method, although you send a couple of words to Google. It will request a URL like this, with usually question marks in between. Let's say, in this case, you search monkeys and banana. In the URL field of the HTTP request, see this field, you will send something like this. This is also one way to send data to the server. You don't have to use post method. But of course, for input forms or for web servers that require a lot of data, post method is commonly used. There is also this put method. The difference between put and post is that in the put, you replace whatever is existent in the server, whereas in the post, you're not replacing it. You're simply sending additional data. And in the head method, instead of requesting everything, like in the get, in the head method, you are only requesting some information about that web page. So you don't want to download everything, but maybe you want to download the size. You want to know what's the length of that file, content length of that file. Okay? So these are some of the HTTP request messages. But the most common one, obviously, is the get one, is the get method. Now this is the HTTP response message. This is the response to your get, post, put, or whatever request message you have. It is structured very similarly. Again, we have HTTP version 101. And interesting thing we see here is the 200 OK. So this 200 OK means that the message is received, and I will respond to that. There are other codes, like 404 not found, or 400 bad request type of things I'm sure you've seen when browsing the web. Some details about the date, the server, accepted ranges, and the content length. For instance, in the head method that I showed just earlier, as here, you might just request this content length instead of requesting everything in that. And there is also this keep alive field. It tells you how long it is going to keep that TCP connection alive. Again, content type, some carriage return line feed, and then it sends you the data. So this data can be the HTML file, it can be an image, it can be anything referenced by that HTML file and stored on that server. All right? These are some of the status codes. We have already seen the 200 OK code, but by the way, I'm just giving them as an example, just for you to relate these. This is not for memorization, obviously. But I'm sure you've seen the 301 code and the 400 and 401 codes before. So these are some of the codes defined, again, in the RFC documents, the request for comments documents. And as we have seen, that those status codes appear in the first line in server to client respond message. This one, that 200 OK. Okay, now, so here's an example for you to try out the HTTP on the client side for yourself. I'm going to demonstrate it here also. But unfortunately, I cannot get admin privileges on this, so I couldn't activate Telnet, but I'll do that on my Mac here. Top HTML. Or maybe let me just explain it first. So Telnet is a very basic user command, and it uses the TCP/IP protocol for accessing remote computers. Okay, so instead of using a browser to send a GET request to some web server, I will now use Telnet. Well, obviously, your browser already includes this full request message itself. Once I enter a URL there, it puts that URL here, and then it sends this request message. It compiles that request message itself. But with Telnet, it is a very basic protocol, so I will need to write everything myself. So I'll write this command that calls the Telnet application. And I'm sending a request to this website. It could be any website, but this is something I chose. You can choose some other website. So this is the host name, the server, and the host name and the URL I'm calling is the same, so I'm leaving this empty here. And I'm connecting it at port 80. Why 80? Because 80 is the port number for the HTTP protocol. And you can check this website out yourself right now. What this website displays is your IP address. So if I show it here, give me a moment. Okay. Check ip.dynDNS.org. Okay. So if you look at this website, it sends you a very simple HTML file telling you your IP address. Okay? So now I'm going to connect to this web server without using, all right. Oops. Without using my browser. If you want to do this on your Windows computers, you need to activate Telnet first through the command center. If you're doing it on your Mac, you need to download Telnet. I did it using Homebrew, but there are other methods as well. So let's switch to my laptop. Okay. So now, oops, I was already connected. We just terminate it and open another one. It's a little bit small, but I hope you can see. So what I'm doing is I'm just writing the command on the slides, nothing else. That is telnet check ip.dynDNS.org 80 at port 80. So now I initiated a connection there. My TCP connection is live. So I'm now sending an HTTP request message. Get, I'm requesting for the base HTML file, so I'm leaving this empty after that slash character. HTTP //101. I press enter, and host, the host name I'm connecting, check ip Okay, so this is running some script in that website. Connection closed by service unavailable. Why is that? Oh, maybe I was too slow. Let me try again. Maybe close the connection, the TCP connection. I'm going to be faster this time. Get /http /101 host check ip.dyn_dns.org. Oops. Okay, maybe it doesn't work in here. I don't know. Maybe it is blocked somehow, telnet by NUS network, or maybe I'm too slow, but it worked at home. Anyway, you can try this at home. One thing you need to remember is that telnet only supports HTTP, so you cannot connect to a web server if it doesn't support HTTP but HTTPS. Some web servers only require secure connection, so you cannot connect to them using telnet. All right? Okay, so I'm going to stop here for today. So the next time we're going to look at the cookies and the web cache. But any questions on today's lecture? Okay, then I'll see you on Friday.